Hello and welcome to my presentation for Lab 4, where we're looking at spring physics. In this lab, we were asked to analyse video footage in Tracker, create a computational model, graph the motion and energy changes of the model and of the data, and compare data from the model and from the video. In this lab, we use Newton's second law to compute the ball's movement, and we use the energy principle to graph the energy changes. Using Tracker, we first set the distance using a known length of 0.7 meters between the fixed attachment point and the mass. We also set the origin at the fixed attachment point. On the right, we can see the motion of the mass, and we exported the x and y data into a CSV file, which we'd use later in our model. In order to create a computational model, we first need to set the initial conditions. We're going to model the object as a ball, and we set its mass, initial position, and initial velocity here. We also set the delta t, used later in the calculation. Here we set the value for g, calculate the spring constant and the relaxed length of the spring. And we also calculate L, the length of the spring, as well as L hat, the direction, and S, which is the extension of the spring. Before entering the calculation loop, we will calculate the kinetic energy, the gravitational potential energy, and the spring potential energy, as well as the total energy. During each iteration of the calculation loop, we will calculate values for the force due to gravity, the force due to the spring, and F net, as well as updating the ball's velocity and the ball's position. We will also calculate the change in each type of energy during each iteration of the loop. Here we can see the outputs of the model. We can see the path the ball took over the entire time period, as well as the forces which act upon the ball. It's worth noting that the spring force acted in the positive y direction for the entire time period, meaning the spring length was never less than the relaxed length. On the right, we can see the model data in blue and the tracker data in red. As the oscillation periods line up, the spring constant must have been accurate, but as the amplitudes are slightly different, the relaxed length used in the model is likely incorrect. On this graph, we can see the kinetic energy in blue, the gravitational potential energy in red, the spring potential energy in green, and the total energy in orange. We'll come back to this graph momentarily. Now, looking at the final questions. This first question asks us to determine whether the energy principle is satisfied. As the kinetic potential and spring potential energies sum to a constant value, shown by the orange flat line, the energy principle is satisfied. We're next asked to produce two estimates for the oscillation period using the x and y data from Tracker. The two calculations of the period are similar but slightly different. Whilst I'm not 100% sure, I think the difference is down to an error plotting the point masses in Tracker before. Thank you for listening.